Bridges, majestic, complex, essential. Bridges, a national problem, estimated at $41 billion. Have you ever felt the vibrations of heavy traffic, vibrations that go right through you as you drive over a bridge? Every day, millions of people in cars and trucks pound away at our nation's 565,000 bridges. Thousands of commuters and freight trains rumble over our railroad bridges. The pounding never stops, but every driver assumes the bridge is safe. You assume it's safe because current inspection information leads you to that conclusion. With 50 years as the useful life of a bridge, over 11,000 need replacing every year. Currently, 200,000 are deficient, and over 98,000 are structurally weak and must be closed, restricted, or immediately rehabilitated to prevent collapse. An estimated 150 bridges do collapse every year, taking 12 lives. The 1967 collapse of the Silver Bridge, killing 45 people, focused national attention on bridge conditions. Congress passed legislation which, while providing some funding to states, requires that each state inspect its bridges at least once every 2 years. According to the Bridge Inspector's Training Manual, bridge inspectors must make objective and subjective observations and transcribe these observations into a written report format. This information must be in sufficient detail to give a clear and complete picture of all the conditions that currently exist on every component on every bridge. That's for each of the 565,000 bridges in the nation. 8 to 13,000 bridges per state. Imagine the difficult and time-consuming task of documenting in words, drawings, and even photographs the condition of just one component. To do the same for hundreds of components on thousands of bridges makes the job impossible. It can't be done, but it has to be done, not only because it's the law, but because bridge safety is a matter of life and death for millions. The time, manpower, and money just aren't there. So with current bridge inspection methods, the type of information we must settle for is inadequate to give a clear picture of the bridge. Typically, components are lumped together and conditions described with numbers such as 9 for new and 0 for conditions beyond repair and in danger of immediate collapse. The essential completeness of narrative descriptions is reduced to a few words like paint, corroded, or laminating rust. Photographs are an excellent format for quickly and accurately recording a component's condition. But this format is not compatible with a written inspection report format. Close-up photographs which show detail like this must leave a lot of doubt as to what the component is or its location relative to the whole structure. The inherent format incompatibility can lead us to wonder if the detailed photo is matched to the correct report. The poorer the information, the greater the risk of catastrophe. In fact, the Bridge Inspector's Training Manual states, information contained in many reports has unfortunately not always been sufficient, nor has it been in a form suitable for analysis and evaluation. So in order to report on all the components, we must first be able to observe them closely from a proper point of view. Until now, access to critical components located on the underside of the bridge was provided by trucks with personnel carrying baskets located at the end of articulated arms operating from the bridge deck. Even a small accidental impact of the inspection truck during operations under the bridge could be fatal to the inspectors. So mobile barricades like these trucks are used to protect the inspection truck. That involves more people, equipment, and money. The time-consuming process of setting up and moving the arm through the truss sections causes vital traffic lanes to be blocked, resulting in traffic jams miles long. The impact to the motoring public is enormous. According to projections from Texas A&M University, this scene, repeated on only 10% of the heavily traveled bridges in the nation, costs the public over $39 billion every year in time and fuel loss. $39 billion. The whole bridge problem is only estimated to be $41 billion. But is it worth it? Not really, because the arms of the inspection trucks are generally inadequate to get personnel far enough under or high enough to view all the components with a necessary line of sight. These drawings in the Bridge Inspector's Training Manual show a line of sight looking down. This is the line of sight required to make such observations. In the field photographs from the same manual, our line of sight is looking up. The problem is the flange blocks our view of the web, as we can see here. In fact, major holes which occur at the web and flange like this cannot be observed from below. The first several inches of the web and, of course, the shelf created by the flange are completely unobservable. This is the shelf that collects salt and other corrosive materials that accelerate the decay of the steel components. What we have is a critical need for access and information. But the lack of time, money, and access currently force us to work with an inherently inadequate reporting system. The result is the needless waste of billions of dollars of fuel and human lives. During a typical inspection in 1982, one of two inspectors risked his life by leaving a catwalk and creeping out on a floor beam to get a better look at a pin and hanger assembly. However, while he was able to make a hands-on inspection, he was unable to make a proper visual inspection. The 1-inch space caused by the hanger falling off the pin was not felt or seen. He and the other inspector observed the other pin and hanger assemblies using binoculars from 20 feet away. This component's condition was lumped together with those of other bearings and was reported to have laminated rust. The National Transportation Safety Board states, neither inspector noticed the change of dimensions that was observable, and an opportunity to detect the problem and prevent the collapse was missed. The observations recorded by the safety inspectors during the September 1982 and previous inspections were inadequate to describe the actual condition of this bridge at the time of the inspection. The undetected problem with the component was the probable cause of the collapse. That critical pin and hanger component failed on July 28, 1983 at 1:30 in the morning as people were moving at highway speeds on the bridge over the Mayanas River. The failed component allowed a 100-foot span of bridge to collapse, creating this void. 2 trucks and 1 car, unable to stop in time, fell with the span. A 3rd car did stop in time, but a 4th did not, and also plunged 7 stories into the void. The direct and instant loss from the collapse was $16 million in bridge damage, 3 people seriously injured, and 3 fatalities. Architectural Telescans Incorporated began work in 1982 with a team of highly qualified professionals developing a robotic bridge observation and information system. The result of ATI's effort is an information system so unique it's considered proprietary nationally and internationally. ATI begins by accurately loading the DOT's general bridge drawings into ATI's computer-aided design programs. ATI's structural engineers then design a compatible delivery system and submit the entire design for the DOT's approvals. First, permanent track that runs the full length of the bridge is designed for installation on both sides. Second, a space frame is designed that will span the full width of the bridge. Next, transmission drives are added to each side of the space frame. This space frame provides vibration damping support for a transversing car, which carries a turntable. Finally, computer-controlled robotic arms are installed. The entire assembly can be delivered to the underside of the bridge using the waterway and simple flotation tanks, then lifted into place with cables like a swing stage scaffold without disrupting traffic. Once in place, the transmission drives engage the track and traffic is never disturbed. The low profile of the robotic arms in the closed position lets the delivery system move easily under the floor beams, giving access to the length of the bridge. When the obstacle of a pier is reached, the delivery system is lowered to the water, floated around, lifted, and re-engaged to the track. Again, traffic is never disturbed. The transversing car gives full access from side to side of the bridge, moving easily under the cross-bracing. The robotic arms deliver high-resolution color TV cameras to the locations that give the best line of sight, with computer accuracy time after time, inexpensively and safely. Other payloads include sandblasting and painting equipment and non-destructive testing devices. The robotic arms blossom open to deliver payloads high up into the spaces between the beams to provide a line of sight never before achievable. ATI's system has unsurpassed access to the bridge components while providing a permanent time-dated record at the rate of 30 frames per second. The system delivers large, clear overviews while zoomed out, or with high magnification, allowing the smallest of faults to be detected. Important information on every component is collected in seconds of real time and can be viewed, understood, and shared with objective reality in the comfort of your office with the ATI reader. At the reader, you are in control. You can quickly move through ATI's telescans at high speed in forward and reverse, or from frame to frame in slow motion. You can stop at any frame and view it closely without distortion. Compatibility of format is achieved with a keyboard, where you can type text of notes, work orders, and sufficiency ratings right over the picture. But what about location? How do you know where a given view is relative to the whole of the structure? ATI has programmed a personal computer to act as a location plotter. A coordinate signal sent out by the ATI delivery system becomes an identification point on the same 20-megabyte hard disk the bridge drawings are on. So with computer and video telemetry running together at the reader, you can fade in and magnify the bridge floor plan and locate the operating position of the camera. The integration of computer-generated bridge drawings and telemetry together allow you to identify problem areas and take appropriate action. The ATI telemetry system is also mounted in helicopters to provide the same important information for deck and superstructure conditions. Architectural Telescans is more than a provider of hardware. ATI is a team of professionals. Engineers, PhDs, managers, experts in electronics, robotics, systems, and software. We are a management resource ready and able to install, operate, maintain, and customize equipment to each application. ATI's technology brings down the cost of bridge observation while vastly improving the quality of the information. Imagine being able to see into every nook and cranny, inches from every surface, yet be safe and comfortable on the ground. Imagine being able to observe and perform non-destructive tests high into the void air spaces of a structure in any weather without taking even one lane of traffic from the bridge, moving fast from point to point, doing in hours what used to take days. Imagine being able to capture the image of a surface and obtain NDT sensory results so systematically that years from now you could track the growth of a crack and even project the growth of a flaw with computer projections. Imagine the objectivity of having time, date, and accurate location information inseparably combined with the observation image, all recorded at the instant of observation. Imagine what ATI can do for you today and tomorrow.